Dear students, we have seen in part 1 about the spectrum of an element x of a and the resolvent equation. Now we are going to prove in this part 2 that spectrum sigma of x is a non-empty subset of C. So the contents. We will prove that spectrum sigma of x is non-empty. Then we shall define spectral radius of x. Then we will give the definition of division algebra, and then we will prove a small result known as Gelfand theorem finally. This is a very important theorem. Theorem 67a, sigma of x is non-empty. In other words, the spectrum is a non-empty subset of the complex plane C. What is sigma of x? By definition, sigma of x is equal to set of scalars lambda such that x minus lambda 1 is singular. Okay, we shall prove this theorem. To prove the theorem, first define a function x from rho of x to a. Rho of x is the resolvent set of x. Okay, so x of lambda, where lambda belong to rho of x, is equal to x minus lambda 1 power minus 1. It is a vector, okay, inverse of a vector in a. So x takes an element here. X takes an element lambda in rho of x to the right hand side, a vector in A. By theorem 65c, x of lambda is continuous. Okay. Now x of lambda equal to x minus lambda 1 power minus 1. We can take lambda outside to have lambda power minus 1 into x by lambda minus lambda by lambda 1, that is 1 only, power minus 1 for lambda not equal to 0. Okay, we have already seen. But as lambda tends to infinity, here we have 1 by lambda which tends to 0. So 0 into the vector is 0. So the right hand side tends to 0 as lambda tends to infinity. And so the left hand side x of lambda also tends to 0 whenever lambda tend to infinity. Okay. Now as usually we take two scalars lambda and mu in rho of x. The resolvent set of x, two complex numbers lambda and mu. Then we can compute the resolvent equation. Okay, we have already derived the resolvent equation, the similar one. That is, x of lambda can be written as x of lambda into the vector x minus mu1 and its inverse. Okay, vector and its inverse will reduce to 1. So 1 into x of lambda is the same thing. And we can rearrange this. This is by definition, the last part will become x of mu. So x of lambda into x of x minus mu1 is written as x minus lambda 1 plus lambda minus mu of 1. Okay, both are same because this minus lambda 1 will get cancelled with plus lambda 1 to leave x minus mu 1 the same thing here, x of lambda, sorry, x of mu. Okay, that is, we can bring x of lambda inside, x of lambda into x minus lambda 1 plus lambda minus mu scalar into x of lambda into x of mu. So therefore, that is equal to, we can write x of lambda minus x of mu equal to lambda minus, actually this part becomes 1, okay, because x of lambda equal to x minus lambda 1 power minus 1, in the same way it will become 1 into 1 plus lambda minus mu into x of lambda into x of mu. So we can bring x of mu inside to have this is 1. So 1 into x of mu is x of mu minus lambda minus mu into x of lambda into x of mu. Okay, so that x of mu can be taken to the left hand side to have x of lambda minus x of mu equal to lambda minus mu into x of lambda into x of mu. Take it as 2. Now we will take a functional on A. Let f be a functional on A. Okay, or we can say f belong to A star. Okay, f is in A star or f is a functional on A. Okay, we define f of lambda by f of lambda equal to f of x of lambda, where lambda belong to rho of x. Since f is a functional and x of lambda is continuous, clearly f of lambda is continuous on the resolvent set rho of x. Okay. Now here f of lambda is defined to be f of lambda equal to f of x of lambda, which is a composite of two continuous functions. F being a functional which is continuous, x of lambda, we have already shown x of lambda equal to x minus lambda 1 power minus 1, which is also continuous. So it is composite of two continuous functions, again continuous. So f of lambda is a continuous function on the resolvent set rho of x. Okay, right. But from 2 we know that x of lambda minus x of mu, that is resolvent equation, equal to lambda minus mu into x of lambda into x of mu. So we can apply both sides f. Okay, f of the vector is equal to f of the right hand side vector. Okay. But if it's a linear functional, we can bring it inside f of x of lambda minus, we can separate linearly, minus f of x of mu equal to this scalar can be lambda minus mu can be taken outside, lambda minus mu into f of x of lambda into x of mu. That is, but what is definition? F of x of lambda is f of lambda. So this becomes f of lambda, this becomes f of mu. So f of lambda minus f of mu equal to lambda minus mu into f of x of lambda into x of mu. Divide by lambda minus mu. So division by lambda minus mu gives equal right hand side is f of x of lambda into x of mu. Okay. Now take both sides, limit as lambda tends to mu. So limit as lambda tends to mu, the left hand side equal to limit as lambda tends to mu, the right hand side. Okay. But what about the right hand side? If we take lambda to be mu or replace lambda by mu, we have x of mu into x of mu the whole square. So limit of lambda tends to mu, limit as lambda tends to mu, f of lambda minus f of mu by lambda minus mu is equal to f of x of mu the whole square. Okay. Limit exists, or this is nothing but the differential coefficient. Limit is nothing but what? F dash of lambda at lambda equal to mu. The left hand side is nothing but f dash at lambda equal to mu, derivative. Okay. So this shows that f of lambda has a derivative at each point of rho of x. Okay. Again, by definition of f of lambda equal to f of x of lambda. So we can take modulus of f of lambda equal to modulus of f of x of lambda, that will be less than or equal to norm of f into norm of x of lambda. We know that norm t of tx less than or equal to norm t into norm x. Similarly, okay. So modulus of f of x of lambda will be less than or equal to norm f into norm of x minus lambda. But already we know x of lambda, okay, already x of lambda tends to 0, isn't it? By 1. By 1, x of lambda tends to 0 as lambda tends to infinity. So x of the right hand side, norm of x of lambda also tends to 0 as lambda tends to infinity. So this is 0. So right hand side fully tends to 0 as lambda tends to infinity. But it is modulus of f of lambda less than or equal to which tends to 0. So norm tends to 0 means f of lambda tends to 0. So modulus f of lambda tends to 0 as lambda tends to infinity. Okay. Even though the complex number, okay, approaches infinity, f of lambda, the function, tends to 0. What does that mean? This function is a bounded function. F of lambda is bounded. Now, to prove the theorem, we have to, that is theorem statement, theorem statement is to show that sigma of x is non-empty. Okay. If possible, assume the contrary. That is, assume that sigma of x is empty. So what will happen if sigma of x is empty? I have already mentioned that sigma of x is the spectrum of x in A, which is a subset of the complex plane. Okay. Rho of x is its complement of sigma of x. So rho of x union sigma of x, or sigma of x union rho of x, is nothing but the entire complex plane C. If sigma of x is empty, means rho of x is the entire complex plane C. Okay. So rho of x becomes C. C equal to rho of x. Okay. Since f of lambda has a derivative at each point of rho of x, that is each point of C, at each point of C, f of lambda is analytic everywhere. F of lambda has a derivative at each point of the complex plane, or we can say f of lambda is analytic everywhere in the complex plane C. We know that a function which is analytic everywhere is called an entire function. So thus f of lambda becomes an entire function. Okay. Already f of lambda is bounded. Now it is an entire function. So f of lambda is a bounded entire function. F of lambda is a bounded entire function. But what Liouville's theorem says, it is one of the important theorem of complex analysis, which states that if a complex function is entire, that is analytic everywhere, unbounded, then it will be a constant. Just it reduces to a constant only. So because f of lambda is an entire function as well as it is bounded, by Liouville's theorem f of lambda must reduce to a constant. But we have shown in the previous slide that f of lambda tends to 0 as lambda tends to infinity. Hence at one point it tends to 0 if it is also constant, so it should be identically 0. F of lambda must be identically 0 for all lambda belong to rho of x. But by definition of f of lambda is nothing but f of x of lambda. So that implies f of x of lambda is identically 0 for all lambda where lambda belong to rho of x. Okay. Since f is an arbitrary function on A, by theorem 48b, that is a corollary to Horn-Banach theorem, we must have x of lambda should be 0 for all lambda. Okay. But actually what theorem 48b says, whenever there is a non-zero vector in the non-linear space, if it is non-zero, correspondingly we can get a non-zero functional f. Okay, that is the essence of the theorem 48b. Here, if for any functional f of x of lambda equal to 0 for all lambda means, then by theorem 48b saying in other words, all the vectors should be 0 or x of lambda must be 0 for all lambda. Okay. What is x of lambda? X of lambda is nothing but x minus mu1 power minus 1. So x minus mu1 power minus 1 is 0. Now 1 is equal to x minus lambda 1 into x minus lambda 1 power minus 1, a vector and its inverse. Okay. So that will automatically become 1. So 1 is equal to, we can write it as a vector and its inverse. But this part is 0. So 0 into the vector is 0. So we finally got 1 equal to 0, which is absurd. How can we have 1 equal to 0? So this contradiction arises only because of our assumption that lambda x is empty. So it should be wrong. Our assumption should be wrong. So lambda x should be non-empty. Okay. And proof is complete with this. Now we will prove one more theorem. The theorem is named after Gelfand. For that we define two main definitions. First definition, spectral radius of x. The number r of x defined by r of x is equal to supreme of mod lambda, where lambda belongs to sigma of x, is called the spectral radius of x. Okay. So spectral radius of a vector x of a Banach algebra is nothing but supremum of mod lambda, where lambda belongs to rho of x. Actually, what is rho of x? Rho of x having complex numbers lambda such that x minus lambda is singular. Collect all those lambdas, consider the scalar values, modulus of those complex numbers, take the supreme of that, that is defined to be r of x or otherwise spectral radius of x. Since sigma of x is contained in the closed disk mod z such that mod z less, z such that mod z less than or equal to norm x, it clearly follows that r of x will also satisfy the same inequality. So 0 less than or equal to r of x less than or equal to norm x, or the spectral radius lie between origin and norm x. Next, division algebra. A division algebra is an algebra with identity in which each non-zero element is regular. So division algebra is nothing but a Banach algebra with identity, having an identity element 1, in which every non-zero element is invertible or every non-zero element is regular. Okay, right. Next we pass on to theorem B. This is due to Gelfand. If A is a division algebra, then it equals the set of all scalar multiples of the identity. Scalar means lambda, identity means 1. So scalar multiple of lambda is lambda into 1. Okay, so we have to show that x is equal to lambda 1. What is x? If x belongs to A is arbitrary. Okay, so we have to show that if x belongs to A is arbitrary, then x is equal to lambda 1 for some lambda. And then this theorem will follow at once. Suppose assume that this is not the case, or x cannot be equal to lambda 1 for any lambda. Assume that, on the contrary, assume that x is not equal to lambda 1 for any lambda. If x is not equal to lambda 1 for any lambda, means x minus lambda 1 not equal to 0 for any lambda, or x minus lambda 1 is regular. If it is 0 means it is singular, not equal to 0 means it is regular. X minus lambda 1 is regular for every lambda. So for every lambda, x minus lambda 1 is regular means sigma fx is empty. Okay, but this is a contradiction to the previous theorem 67a, an important theorem, which theorem states that in a complex plane, sigma fx is non-empty. Okay, non-empty subset of the complex plane. So this contradiction arises because our assumption that x minus x not equal to lambda 1 is wrong. There exists some scalar lambda for which x is equal to lambda 1. So given any x belong to A to be an arbitrary element of A, that always can be written as a scalar multiple of 1. Okay, so that is what the theorem says. If A is a division algebra, then it should equal the set of all scalar multiples of the identity. Okay, that's all. Thank you. We will see one more part for this section that is not so important. If time permits, I will be giving presentation for this also, or otherwise I will be going into the next section 68, which is very important. Okay, so meet you then.